Gravity is the most familiar mystery in the universe. It is there before anything is explained. It is there in the simple heaviness of your body against the bed, in the quiet fall of rain against a window, in the moon lifting the oceans by a fraction, and in the immense patience of planets circling the sun. It holds the atmosphere close to Earth, gathers gas into stars, bends the path of light, and shapes the largest structures ever observed. And yet, the more carefully physics has studied gravity, the less it has behaved like the ordinary force it seems to be. A push feels like a force. A pull feels like a force. The tension in a rope, the pressure of a hand, the shove of wind against a door, these all feel direct and obvious. Gravity seems to belong in the same family. Drop a spoon, and it falls. Step onto a scale, and it gives a number. Jump into the air, and Earth rather politely refuses to let the arrangement continue for very long. But beneath that everyday experience is a much stranger idea. In Isaac Newton's picture, gravity was a force of attraction between masses, a universal pull reaching from apples to moons to planets. It was one of the greatest ideas in the history of science, and it still works beautifully for much of ordinary life. Then Albert Einstein changed the question. In general relativity, gravity is not described as a normal force, pulling objects through space. Instead, matter and energy change the shape of spacetime itself, and objects move along the natural paths created by that curved geometry. A planet orbiting a star is not quite being dragged around by an invisible rope. It is travelling as straight as it can through a universe whose geometry is no longer flat. So, the strange answer is this. Gravity feels like a force because the floor, the ground, or the chair beneath you is stopping you from following your natural path through space-time. The thing you feel as weight is not simply gravity pulling down. It is the world pushing back. Welcome to the Sleepy Scientist. It is very good to have you here. Before settling into tonight's journey, take a moment to notice where you're watching from. Maybe it is late where you are. Maybe the room is quiet, the lights are low, and the outside world has finally softened around the edges. Maybe you're tucked into bed, half listening already, or resting on a sofa with a cup of tea that has chosen, with great scientific precision, to become drinkable at the exact moment your attention wanders. Wherever you are, I hope you are comfortable, safe, and ready to drift gently into one of the deepest ideas in physics. If you enjoy calm scientific stories like this, a like and a subscribe really help the Sleepy Scientist keep floating along. And to everyone already subscribed, thank you. Truly. Your support means a great deal, especially for a channel devoted to explaining the universe at a volume that does not frighten the furniture. Tonight's question sounds almost ridiculous at first. Why gravity is not really a force. So let's begin gently with the familiar feeling of weight beneath you and follow it outward to falling objects, orbiting moons, curved space-time, black holes, gravitational waves, and the quiet realization that the force you feel every day may not be quite what it seems. Gravity is one of the first laws of the world you ever learn, long before anyone explains it. It is there in the body before it is there in the mind. It is there when a child drops a toy from a high chair and watches it fall, again and again, with the calm seriousness of a tiny experimental physicist who has discovered peer review by repetition. It is there in the heaviness of tired legs after climbing a long flight of stairs, in the careful balance of a cup on a table, in the way rain returns to the pavement, and in the way every jump ends with the ground arriving beneath you. Gravity feels obvious because it is constant. It does not flicker on and off. It does not need to be noticed before it works. A person can forget about gravity completely, and gravity will continue managing the situation with quiet confidence. It keeps oceans wrapped around the planet, holds the atmosphere close to Earth, pulls rivers downhill, shapes mountains under their own enormous weight, and keeps the moon moving around Earth in a slow, steady rhythm. From ordinary experience, it seems natural to call gravity a force. It behaves like one. It pulls objects downward. It gives weight to the body. It makes balance necessary. It makes climbing harder than walking across level ground. It makes a dropped cup fall, and if that cup happens to be full of tea, gravity also becomes briefly involved in home decoration. This everyday picture is powerful because it is useful. When you stand on the floor, you feel your weight pressing downward. When you lift a suitcase, your muscles must work against something. When you climb a hill, the body understands, without needing any equations, that upward is different from sideways. Gravity seems to be a downward pull from Earth, as if the planet has invisible hands gently but firmly insisting that everything nearby should stay close. That simple picture is not foolish. It is how gravity appears in daily life, and for many practical purposes it works extremely well. Engineers, pilots, athletes, builders, and anyone carrying shopping up a steep path can all treat gravity as a force and get along perfectly well. Near Earth's surface, the acceleration caused by gravity is about 10 meters per second, which means a falling object gains speed rapidly if air resistance does not interfere. That is a real measurable effect, not a poetic suggestion from the universe. But physics has a habit of beginning with what feels obvious, and then gently revealing that the obvious thing was only the surface. Heat feels like a substance flowing into the skin, but it is more deeply connected to the motion of atoms and molecules. Colour feels like a property sitting inside objects, but it depends on light, surfaces, eyes, and the brain. Sound feels as if it travels whole through the air, but it is really a pattern of pressure waves moving through a material. In the same way, gravity feels like a straightforward pull, but the deeper explanation is stranger. The important distinction is between experience and mechanism. Experience tells you what something is like from the inside of ordinary life. Mechanism asks what is physically happening underneath that experience. Both matter. The feeling of weight is real. Falling is real. Tides are real. The moon's influence on Earth's oceans is real. None of that disappears when physics says gravity is not really a force in the deepest modern sense. That phrase can sound misleading if it is heard too quickly. It does not mean gravity is fake. It does not mean gravity is imaginary, optional, or somehow less real than other parts of physics. Gravity is one of the most important features of the universe. Without it, there would be no planets, no stars, no galaxies, no long-lived worlds, and no comfortable place for a sleepy scientist to place a mug. The point is more precise than that. Modern physics describes gravity differently from forces such as electromagnetism. Electromagnetism is the interaction responsible for electric charge. Magnetism, light, chemistry, and the contact forces between ordinary objects. When a hand presses against a table, atoms in the hand and atoms in the table resist being pushed through one another because of electromagnetic interactions. That contact force is very real, and it is the reason solid things do not simply pass through other solid things in a very inconvenient and alarming way. Gravity, however, becomes something else in Albert Einstein's general relativity. In that theory, gravity is not described as a normal force pulling objects through space. Instead, matter and energy affect the shape of spacetime, and objects move along the natural paths created by that curved spacetime. The object is not always being tugged away from its proper path. In many cases, it is following its proper path, but the geometry around it is not the simple, flat geometry everyday intuition expects. This is the central tension. In daily life, gravity behaves like a force. In Isaac Newton's physics, gravity is treated as a universal force of attraction between masses. Newton's theory is one of the greatest achievements in scientific history because it showed that the same principle could explain falling objects on Earth and the motion of the moon around Earth. The heavens and the ground were no longer separate realms with separate rules. They were part of one physical system. Newton's gravity still works brilliantly in weak gravitational fields and ordinary speeds. It can describe the arc of a thrown ball, The fall of a stone, the motion of planets, and the timing of many spacecraft journeys with astonishing accuracy. For everyday purposes, it is not merely good, it is magnificent. But Einstein looked at gravity differently. His theory did not simply adjust Newton's numbers, it changed the meaning of the situation. A falling object in general relativity may not be experiencing a gravitational force in the ordinary sense. It may be moving freely through curved space-time. The surprising thing is not that it falls. The surprising thing is that the ground stops it. That is why standing still can be more mysterious than falling. A person standing on Earth feels weight because the ground is pushing upward, preventing the body from following its natural freefall path. In a freely falling lift, or inside an orbiting spacecraft, that feeling of weight can vanish, even though gravity has not vanished at all. Astronauts in orbit are not beyond Earth's gravity. They are falling around Earth continuously, moving forward fast enough that they keep missing the ground. It is a wonderfully elegant arrangement, though perhaps not one to attempt casually from a stepladder. So the force you think you know is already more subtle than it first appears. Gravity is familiar enough to be ignored, yet deep enough to reshape the meaning of space and time. It is the reason objects fall, but it is also the reason planets orbit. Light bends, clocks tick at different rates, and the universe gathers itself into stars and galaxies. To understand why gravity is not really a force, the journey has to begin with this simple admission. Ordinary life teaches gravity through weight, falling, balance, and return. Physics begins there too, but then it asks a quieter question. What if the feeling of being pulled down is not the deepest part of the story? What if gravity is not something dragging objects away from straight paths, but the shape of the paths themselves? Falling seems simple because it happens too quickly to argue with. Let go of a stone, and it drops. Let go of a coin, and it drops. Let go of a feather in an ordinary room, and it drifts down more slowly, as if gravity has decided to treat it with a little more ceremony. To the eye, this feels obvious. Heavy things fall fast. Light things fall slowly. The world appears to teach that lesson every day, usually with great confidence, and sometimes with the assistance of a biscuit crumb tumbling from a plate. For much of human history, that intuition felt natural. It seemed reasonable to imagine that heavier objects were somehow more eager to reach the ground, while lighter objects were less committed to the journey. But the history of physics is full of moments when careful observation begins to disturb common sense, not by being dramatic, but by being annoyingly precise. Galileo Galilei was one of the people who helped make that disturbance impossible to ignore. Born in Pisa in 1564, Galileo lived during a time when old ideas about motion were being questioned with increasing boldness. He did not invent curiosity about falling bodies, and he was not the only person thinking carefully about motion, but his work helped shift science toward experiment, measurement, and mathematical description. Instead of accepting that heavy objects must naturally fall faster because that seemed sensible, Galileo asked what actually happened when falling motion was examined more carefully. The most famous story places him at the Leaning Tower of Pisa, dropping objects of different masses from the top to show that they reached the ground at nearly the same time. It is a wonderful image. The tilted tower, the waiting crowd, the old idea falling almost as quickly as the objects themselves. The only difficulty is that historians are not certain the demonstration happened in quite that form. It may be more legend than recorded fact, polished by time into a scene too perfect to resist. Still, the principle connected with the story is real and important. Galileo argued that, if air resistance is removed or made unimportant, objects fall with the same acceleration regardless of their mass. A heavy cannonball and a lighter ball do not fall differently, because gravity gives the heavier one a special private appointment with the ground. In ideal conditions, both accelerate in the same way. That is already strange. It means that gravity is not simply heaviness made active. A heavier object does experience a stronger gravitational pull, but it also has more inertia, meaning it resists changes in motion more strongly. These two facts balance in such a way that falling acceleration is the same for objects in the same gravitational field when air resistance is ignored. The result is beautifully simple, but not at all obvious from ordinary life. The problem, of course, is that falling happens quickly. Drop something from a height, and there is not much time to measure what is going on. Galileo's great practical insight was to slow the motion down. He used inclined planes, allowing balls to roll down slopes rather than fall straight downward. By making the slope gentler, he stretched the motion out over a longer time, making it easier to compare distances and intervals. This was not merely a clever trick. It was a step toward mathematical physics. Galileo found that falling and rolling motion followed regular patterns. Distance, time, acceleration, and motion could be related in a precise way. Nature was not just behaving according to vague tendencies, it was following measurable rules. That matters because it begins to separate gravity itself from the clutter surrounding it. In the everyday world, falling objects move through air, and air is not nothing. Air pushes back. A feather falls slowly not because gravity has forgotten it, but because the feather has a large surface area compared with its weight, so air resistance has a strong effect on its motion. A stone falls more directly because air resistance matters much less by comparison. Remove the air, and the difference almost disappears. A famous demonstration of this happened during the Apollo 15 mission in 1971, when astronaut David Scott dropped a hammer and a feather on the moon. With no atmosphere to create significant air resistance, both fell together and reached the lunar surface at the same time. It was a wonderfully clear experiment, performed on another world, and also a quiet tribute to a question Galileo had explored centuries earlier. The hammer and feather did not fall together because the moon was doing something magical. They fell together because, without air getting in the way, gravity gave them the same acceleration. The heavy object was not more favoured. The light object was not less obedient. Both followed the same simple rule. This is where gravity begins to feel less like the rough downward pull of everyday intuition and more like a deep organising principle. Falling is not random. It is not just the natural impatience of heavy things. It is motion governed by regularity, and that regularity can be studied, tested, measured, and described. Galileo's work helped prepare the ground for Isaac Newton, who would later connect falling objects on Earth with the motion of the moon and planets. But before that great unification could happen, falling itself had to become something worth measuring. The ordinary drop of a stone had to be treated not as a boring event, but as a clue. And that is the quiet beauty of Galileo's insight. Gravity may feel obvious, but falling is not as simple as it first appears. Beneath every dropped object is a hidden order, and once that order is noticed, the ground begins to look less like an ending, and more like the first page of a much larger story. Isaac Newton entered the story of gravity like someone quietly rearranging the furniture of the universe. By the time Newton was working in the 17th century, thinkers such as Galileo Galilei had already shown that motion could be studied through measurement rather than assumption. Falling objects were not just doing what heavy things naturally did. They followed patterns. Projectiles curved through the air in predictable ways. Planets moved across the sky with an order that seemed to hint at hidden rules. The world was becoming less like a collection of separate mysteries, and more like one enormous system waiting to be understood. Newton's great achievement was to show that the same rules could describe both Earth and the heavens. In 1687, Newton published Mathematical Principles of Natural Philosophy, often known simply as the Principia. It became one of the most important books in the history of science. In it, Newton laid out his laws of motion and his universal law of gravitation, giving physics a framework so powerful that it shaped scientific thought for centuries. The first of Newton's laws is the law of inertia. It says that an object at rest tends to remain at rest, and an object in motion tends to keep moving in a straight line at a constant speed, unless something acts on it. This may sound simple now, but it was a profound break from older ideas. Motion did not need a constant cause to keep going. Instead, change in motion needed a cause. A stone sliding across ice, a planet moving through space, or a ball rolling across a floor is not naturally trying to stop because stillness is its proper condition. It stops because something interferes, such as friction, air resistance, or another force. Inertia made motion itself seem calmer and more lawful. Objects were not restless or purposeful. They were obedient to patterns. Newton's second law explained how force changes motion. A force can speed an object up, slow it down, or change its direction. The more mass an object has, the more it resists that change. This is why pushing an empty shopping trolley is very different from pushing one that has been loaded as if someone is preparing for a winter siege. The same push produces a smaller change in motion when the object has more mass. Newton's third law said that forces come in pairs. If one object pushes on another, the second object pushes back with an equal and opposite force. A foot pushes against the ground and the ground pushes back. A rocket pushes exhaust gases downward or backward, and the gases push the rocket the other way. This law made interaction central to classical physics. Nothing simply changed motion by magic. Something acted and something responded. Together, these laws made force one of the great organizing ideas of science. A force was not merely a sensation. It was a precise physical concept, a way of explaining why motion changed. Then Newton turned that idea toward gravity. His universal law of gravitation stated that every mass attracts every other mass. Earth attracts a falling apple. The apple also attracts Earth, though the apple's effect on the planet is so tiny that Earth does not noticeably hurry upward to meet it. The sun attracts Earth. Earth attracts the sun. The moon attracts the oceans. Every piece of matter participates in the same quiet exchange. The strength of this attraction depends on two things: how much mass the objects have and how far apart they are. More mass means stronger attraction. Greater distance means weaker attraction. The law could be written mathematically with astonishing simplicity, but its meaning was vast. Gravity was not a local habit of earthly objects. It was universal. This was the great unification. The apple and the moon belong to the same story. The famous apple story is often told as if Newton saw a fruit fall and instantly discovered gravity in a flash of leafy inspiration. The real history was almost certainly less theatrical. Apples had been falling for a very long time, mostly without becoming scientific celebrities. But the important idea remains useful. Newton asked why an apple falls to Earth, and why the moon does not simply fly away into space. His answer was that both are influenced by the same gravitational attraction. The apple falls straight down because it has little sideways motion. The moon continually falls around Earth because it has enough sideways motion to keep missing the ground. That insight joined the everyday and the cosmic. Falling was no longer just a thing that happened near the surface of Earth. Orbiting was a kind of falling too. The heavens were not made of some separate perfect substance with special rules. The same physics applied above and below. The success of Newtonian gravity was extraordinary. It explained the arc of projectiles, the rhythm of tides, the motion of planets, the return of comets, and the stability of orbits. It helped astronomers predict where celestial bodies would be. It helped engineers understand motion and structure. It became part of the foundation of navigation, mechanics, astronomy, and eventually spaceflight. Even today, Newton's gravity remains wonderfully useful. For many situations, it is accurate enough that using anything more complicated would be like bringing a grand piano to open a tin of beans. It works beautifully when speeds are much slower than the speed of light. Gravitational fields are not extreme, and the required precision is not pushed to the very edge. And yet, inside this magnificent theory, there was a mystery. Newton could describe gravity with stunning accuracy, but he did not fully explain how it worked. Gravity seemed to act across empty space. Earth attracted the moon without touching it. The sun influenced distant planets without a visible chain, rope, wind, or mechanism connecting them. The mathematics worked, but the physical cause remained difficult to picture. Newton himself was cautious about this. He did not pretend to know the hidden machinery behind gravitational attraction. His theory said what gravity did, and it said it with breathtaking power. But why masses attracted one another across empty space was left unresolved. That unresolved question matters because it points toward the deeper problem at the heart of the title. Newton made gravity into one of the greatest forces in science. He showed that it governed apples, moons, tides, planets, and comets with the same elegant rule. But even in his own work, gravity carried a strange silence inside it. It acted everywhere. It explained almost everything. And yet no one could say what was doing the pulling. An orbit can look, from a distance, like a perfect act of balance. A moon circles a planet circles a star. A spacecraft moves around Earth again and again, not falling to the ground, not drifting away into darkness, but somehow remaining in that elegant middle state that looks almost peaceful. It is tempting to imagine orbit as the opposite of falling, as if gravity has been escaped, cancelled, or politely negotiated with. But an orbit is not the absence of falling. An orbit is falling that keeps missing the ground. Isaac Newton understood this with one of the most famous thought experiments in physics, the cannonball fired from a very tall mountain. Imagine gently a mountain so high that its peak rises above most of the atmosphere. From the top of it, a cannon fires a ball sideways. If the cannonball is fired gently, it travels forward for a short distance, curves downward under gravity and strikes the ground. Fire it faster, and it travels farther before hitting Earth. Fire it faster still, and the curve of its fall begins to match the curve of Earth itself. At a certain speed, the cannonball is still falling, but Earth's surface curves away beneath it at just the right rate. The cannonball never reaches the ground, not because gravity has stopped acting, but because the ground keeps slipping away around the planet. This is the basic idea of orbit. It is not a place where gravity is absent. It is a state of continuous free fall around a larger body. This is one of those ideas that sounds strange at first, and then becomes beautifully simple once it settles into place. The moon is falling around Earth. Earth is falling around the sun. Satellites above Earth are falling too, though they are moving sideways so quickly that their fall becomes a circle, or more often, an ellipse. They are not held up by engines. They are not resting on invisible rails. They are moving forward through space while gravity constantly bends their path inward. In Newton's physics, this is the partnership between inertia and gravity. Inertia is the tendency of an object to keep doing what it is already doing. An object at rest tends to remain at rest. An object in motion tends to keep moving in a straight line at a steady speed, unless something changes that motion. A planet, left entirely alone, would move onward in a straight path through space. It would not naturally decide to curve around a star. Planets, despite their many charms, are not known for steering. Gravity changes that. In Newton's picture, the sun exerts a gravitational force on Earth, constantly pulling it inward. Earth's inertia carries it forward, while gravity bends that forward motion into an orbit. The result is not a simple fall straight into the sun, and not a straight escape into space, but a long continuous curve. This same idea helps explain why the moon does not crash into Earth. The moon is moving sideways quickly enough that, as it falls toward Earth under gravity, it continues to miss. Its path is not perfectly circular, but the principle is the same. Gravity keeps altering the moon's direction, while inertia keeps it moving onward. The moon's orbit is the ongoing compromise between straight-line motion and gravitational bending. There is something quietly magnificent about this. The moon does not need a motor. Earth does not need a cosmic hook. The solar system does not require strings, rods, wheels, or a celestial maintenance team with very large ladders. Motion and gravity are enough. The same principle applies to artificial satellites and spacecraft. The International Space Station orbits Earth at an altitude of roughly 400 kilometers. It is common to hear that astronauts are weightless because there is no gravity in space, but that is not true. At the height of the International Space Station, Earth's gravity is still very strong, only slightly weaker than at the surface. If the station somehow lost its sideways motion, it would fall back toward Earth. Astronauts feel weightless because their spacecraft and everything floating around them are all falling together. There is no floor pushing up against their feet in the ordinary way. A pen floats beside an astronaut not because gravity has abandoned the pen, but because the pen and the astronaut share the same freefall motion around Earth. They are falling at the same rate, along the same broad path. This is why weightlessness is sometimes called microgravity, though the word can be a little misleading if it makes the gravity sound almost gone. The feeling of weight has disappeared, but gravity itself remains very much involved. It is conducting the whole performance, just very quietly from underneath the geometry of the motion. Even in Newton's four-space picture, then, gravity is already unlike an ordinary push or pull through contact. A hand pushes a door, a rope pulls a sled, a table holds up a book by direct contact. Gravity does something more subtle. It reaches across space and changes the path of motion, without touching the object in the everyday sense. It does not merely drag things downward. It can hold moons in rhythm, guide planets around stars, and keep spacecraft falling forever around the curve of Earth. That is why orbits are so important to understanding the deeper mystery of gravity. They show that falling is not always an ending. Falling can become a path. It can become a circle, an ellipse, a long, quiet loop through space. The same gravity that makes an apple drop from a branch also keeps the moon travelling around Earth, and Earth travelling around the sun. On the ground, gravity feels like a force because the ground is there to stop the fall. In orbit, the stopping never happens. There is only motion, curvature, and the steady refusal of the falling object to arrive. And once falling can become orbit, gravity begins to look less like a simple downward pull and more like something woven into the shape of motion itself. Newton's gravity was powerful enough to hold the solar system together in human understanding, but it carried a strange silence inside it. The law worked. It explained falling objects, orbiting moons, planetary paths, tides, comets, and many of the motions that had once seemed separate. It turned the universe into something mathematically connected. Earth and sky no longer needed different rules. The same gravitational attraction that drew a stone downward also helped guide the moon around Earth and Earth around the sun. But there was a question hiding beneath that success. How did one object know another object was there? In Newton's picture, every mass attracts every other mass. The sun attracts Earth. Earth attracts the moon. A mountain attracts a person standing beside it, although not enough to make the situation socially awkward. The attraction depends on mass and distance, and the mathematics gives wonderfully accurate results in ordinary conditions. Yet the theory seemed to imply that gravity reached across empty space directly, from one body to another, without anything visible passing between them. This is known as the problem of action at a distance. The phrase sounds slightly theatrical, as if gravity has been caught doing something suspicious behind the curtains. But the problem is a serious one. In everyday life, causes usually seem to travel through contact or through some medium. A hand pushes a cup, a rope pulls a bucket, a wave moves through water, sound travels through air as pressure changes. Even a smell drifting across a room is carried by molecules. Something happens here because something has crossed the space between here and there. Newtonian gravity did not clearly say what crossed the space. Earth and the moon are separated by hundreds of thousands of kilometers. The sun and Earth are separated by roughly 150 million kilometers. Yet in Newton's theory, The gravitational relationship between them appears immediate. The sun does not need to touch Earth. There is no visible chain connecting them, no cosmic pole, no hidden string, no gigantic invisible shepherd's crook keeping the planets in line. The bodies simply attract one another across empty space. Newton himself found this uncomfortable. He was careful not to claim that he had explained the underlying cause of gravity. He had described the rule by which it acted, and he had done so with astonishing success. But he did not pretend to know the hidden mechanism. His famous restraint mattered. Newton was not saying with great confidence that mysterious invisible pulling across a void made perfect philosophical sense. He was saying in effect that the mathematical rule worked, even if the deeper cause remained unknown. That distinction is important. A theory can describe nature extremely well and still leave a deeper question open. Newtonian gravity was not weak, because it had this mystery. It was enormously strong as a predictive theory. But it was conceptually incomplete. It could tell astronomers where a planet should be, but not what gravity truly was. Later physics would find another way to think about influence spreading through space, the concept of fields. Michael Faraday, working in the 19th century, helped make fields physically meaningful. His studies of electricity and magnetism led him to imagine space around charged and magnetic objects as filled with lines of force. These were not just decorative drawings. They represented the idea that the space around an object could have physical structure. A magnet did not simply reach across emptiness to another magnet. Instead, it created a magnetic field, and another object responded to the field where it was. James Clerk Maxwell then gave the field idea a magnificent mathematical form. Maxwell's electromagnetic field theory showed that electricity and magnetism were deeply connected, and that changes in electromagnetic fields could travel through space as waves. Light itself became understood as an electromagnetic wave. This was a profound shift. Influence was no longer imagined only as direct contact between objects. Space could carry physical activity through fields. Even more importantly, electromagnetic effects travelled at a finite speed. They did not act instantly across the universe. Changes in an electromagnetic field spread outward, and Maxwell's theory connected that speed with the speed of light. This made the field concept feel physically satisfying in a way that action at a distance did not. There was something there, not a material substance exactly, but a real physical field that could store energy, carry waves, and influence matter locally. Newtonian gravity, by comparison, still seemed unfinished. It described attraction between masses, but it did not explain the messenger, the medium, or the mechanism. It had no clear account of what happened in the space between the Sun and Earth. Gravity was known by its effects, not by its inner nature. For a long time, that was acceptable because Newton's equations were so successful. When a theory predicts planetary motion, tides, falling bodies, and cometary returns with extraordinary accuracy, people are naturally reluctant to complain that it has not explained absolutely everything. In science, a working equation can be very persuasive. It is difficult to argue with a theory that keeps correctly telling you where Neptune is going to be, especially when Neptune is not known for waiting patiently while philosophy catches up. So, the mystery remained, quietly tolerated. Newton's gravity became the foundation of classical mechanics. It was used, trusted, refined, and celebrated. Its conceptual difficulty did not stop it from being one of the greatest achievements in human thought. But eventually physics began to demand something deeper. The problem was not that Newtonian gravity failed everywhere. It did not. In most everyday situations it worked beautifully. The problem was that it treated gravity as a force without explaining what kind of physical thing made that force possible across empty space. It gave the universe an astonishing rule, but left the stage machinery hidden. That hidden machinery would become the opening Einstein needed. To move beyond Newton, gravity did not simply need a better number or a small correction. It needed a new meaning. It needed a way to understand how one body could influence another without imagining an invisible pull acting instantly through nothing. And that is where the story begins to turn. Gravity had been described as a great force, but perhaps the deeper answer was that gravity was never quite a force in the ordinary sense at all. Albert Einstein came to gravity through a doorway that did not look like gravity at first. In 1905, he published his special theory of relativity, a theory that changed the meaning of space, time, motion, and light. It showed that measurements of time and distance are not absolute in the old Newtonian sense, but depend on the motion of the observer. It also placed the speed of light at the centre of physics, not as an ordinary speed that could be overtaken, but as a fixed limit woven into the structure of reality. Special relativity was astonishing, but it did not yet include gravity. That was a problem, because Newton's gravity still seemed to work across empty space in a way that did not fit comfortably with Einstein's new view of the universe. If nothing could travel faster than light, then gravity could not truly be an instant pull acting everywhere at once. Something had to change. But instead of beginning with planets or stars, Einstein began with a much smaller and quieter question. What does gravity actually feel like? The answer seems obvious. Gravity feels like weight. It feels like the body pressing into a chair, feet resting on the floor, the effort of climbing stairs, the dull heaviness of a suitcase in one hand. But Einstein noticed something subtle. Perhaps what people call the feeling of gravity is not gravity itself. Perhaps it is the feeling of being prevented from falling. This idea became part of what Einstein called the equivalence principle. In its simplest form, it says that the effects of gravity and acceleration are deeply connected. More specifically, a person in free fall can feel locally weightless, in a way that is indistinguishable from floating far away from any planet, star, or moon. Imagine being inside a sealed lift, with no windows and no way to look outside. If the lift were drifting in the deep space, far from any large object, you would float inside it. A pencil beside you would float too. Your feet would not press against the floor. There would be no obvious up or down. Everything would share the same calm, weightless state. Now imagine the same sealed lift falling freely toward Earth. Ignoring air resistance and danger for the moment, everything inside the lift falls together. You fall, the floor falls, the ceiling falls, the pencil falls, and a loose biscuit crumb falls with the full seriousness such crumbs always bring to physics. Because everything is falling at the same rate, you would float relative to the lift. The pencil would hover beside you. Your feet would not press against the floor. Locally, inside that small sealed space, the experience would feel the same as drifting in deep space. That was the startling clue. Gravity can be present and yet not be felt as weight. Person falling freely under gravity does not feel pulled downward in the ordinary way. The feeling of weight appears when something interrupts that free fall. Standing on Earth, the body is not allowed to follow the natural falling path it would otherwise take. The ground gets in the way. The atoms in the floor push against the atoms in the feet through electromagnetic forces. The body feels that upward support as weight. So the strange truth is that sitting quietly in a chair is, in one sense, less natural than falling. A person in a chair feels weight because the chair is pushing upward. A person standing on the ground feels weight because the ground is pushing upward. A person in a falling lift or in an orbiting spacecraft may feel weightless not because gravity has disappeared, but because nothing is pushing upward to stop the fall. Gravity is still shaping the motion, but the body is no longer resisting that motion through contact with a surface. This distinction is easy to miss because ordinary life is spent being stopped by things. Floors, chairs, roads, beds, and staircases all prevent free fall so constantly that their resistance feels like the normal state of the world. Gravity seems like the thing being felt, when much of the sensation is actually the world pressing back. Einstein's insight was radical because it loosened gravity from the ordinary idea of force. A force, in everyday terms, is something you feel as a push or pull. A hand pushes a door, a rope pulls a bucket, a gust of wind presses against a coat. These forces can produce pressure strain, or acceleration that the body notices directly. But gravity was different. In free fall, gravity seemed to vanish from experience, even though it was still present in the motion. That suggested gravity might not be a force that objects feel directly in the same way. It might be something deeper, something that determines the natural paths objects follow when no other force is interfering. The falling lift revealed a remarkable possibility. Maybe gravity is not best understood as a mysterious invisible tug pulling every object downward. Maybe the falling object is doing exactly what it should do. Maybe it is the person standing on the ground who is being forced away from a natural path. This is where acceleration enters the story. Einstein also imagined the opposite situation, a sealed lift accelerating upward in empty space. If the lift accelerated steadily, the floor would press against your feet, and you would feel weight. A pencil released from your hand would appear to fall toward the floor, not because a planet was pulling it down, but because the lift was accelerating upward to meet it. Inside the sealed lift, that experience could feel very much like standing in a gravitational field. Gravity and acceleration then were not merely similar, they were locally equivalent in a deep physical sense. This did not yet give Einstein the full theory of general relativity. It did not yet explain planets, black holes, bending light, or the shape of space-time, but it gave him the doorway. If gravity could be made to disappear locally through free fall, and if acceleration could imitate gravity, then gravity was not an ordinary force placed on top of motion. It was tied to the very way motion itself is described. From that clue, Einstein began moving toward a new picture of the universe. Gravity would no longer be just a pull between masses, it would become a feature of space-time, a sign that the stage on which motion happens is not fixed and flat, but flexible, curved, and shaped by matter and energy. The falling lift was only a thought experiment, quiet and simple, but inside it was one of the greatest turns in scientific history. The feeling of weight was no longer proof that gravity was a normal force. It was the clue that gravity was something stranger. Space and time feel like the quiet background of everything. Space is where things happen. Time is when they happen. A cup sits on a table in space. It falls at a moment in time. A planet moves through the emptiness around the sun, while clocks on that planet tick steadily onward. In ordinary life, it seems natural to imagine space and time as separate things, like two different parts of the stage on which reality performs its usual little drama of falling spoons, cooling tea, and people wondering where they left their keys. For Isaac Newton, this separation made sense. Space was treated as a fixed arena stretching everywhere. Time was treated as a universal flow, passing the same way for everyone and everything. Objects moved through space as time moved forward. That picture is intuitive, and for many everyday purposes it works beautifully. It matches the world as it seems from a quiet room, where clocks behave themselves and rulers do not develop opinions. But special relativity changed that picture. In 1905, Albert Einstein showed that measurements of space and time depend on motion. Two observers moving differently can disagree about the length of an object or the duration between events, and both can be correct within their own frames of reference. This does not mean reality becomes a matter of personal taste. It means space and time are not separate, absolute backgrounds in the old sense. They are related, flexible measurements that depend on the observer's motion. This was deeply strange. A moving clock can tick more slowly compared with a clock at rest relative to an observer. A moving object can be measured as shorter along its direction of motion. Events that appear simultaneous to one observer may not appear simultaneous to another. The universe had not become chaotic, but it had become less simple. Space and time were no longer independent rulers laid across reality. They were connected. Hermann Minkowski gave this connection its most powerful form. In 1908, Minkowski described Einstein's relativity using the idea of space-time. Instead of treating space and time as separate ingredients, He presented them as a single four-dimensional structure. There are 3 dimensions of space, describing left and right, forward and backward, up and down. Time forms another dimension, not exactly like the spatial ones, but inseparable from them in the mathematics of relativity. This is where spacetime became more than a convenient phrase. It became a physical idea. An event is not only somewhere, it is also somewhen. A flash of lightning, the fall of a stone, the orbit of a planet, the arrival of light from a distant star, all have positions in space and positions in time. Relativity describes these not as separate facts, but as parts of one connected structure. The path an object takes through this structure is called its world line, a kind of history traced through space-time. At first, in special relativity, space-time was still flat. Not flat like a sheet of paper, because that image is far too simple, but flat in the mathematical sense that it had no curvature caused by gravity. It provided a new stage for motion, one where space and time were joined. But the stage itself was not yet bending around stars and planets. General relativity took the next step. Einstein's general theory of relativity, completed in 1915, allowed space-time itself to be shaped by matter and energy. The sun does not merely sit inside space while pulling planets from a distance. In Einstein's view, the sun changes the structure of space-time around it. Earth then moves through that curved space-time along the natural path available to it. This is often pictured with a rubber sheet, a heavy ball placed on a stretched surface, making a dip while smaller balls roll around it. The image is useful as a first hint, because it shows how a curved surface can guide motion. But it is also limited. The rubber sheet bends downward because of gravity, so it uses gravity to explain gravity, which is rather like explaining a kettle by saying it is the thing that does kettle behavior. Pleasant, but not quite complete. Real space-time curvature is not simply space bending downward into some visible extra direction. It is a change in the geometry of space and time themselves. It affects distances, durations, paths, and the motion of objects. It tells matter how to move, not by tugging on it like a rope, but by shaping the possible straightest paths through the universe. Those paths are called geodesics. A geodesic is the natural path an object follows when no force is pushing or pulling it away from that path. On the surface of Earth, the shortest route between 2 distant places is not a straight line on a flat map, but a curved path across the globe. Aircraft routes can look bent on a flat map because the map has flattened a curved surface. The path is not crooked from the point of view of the globe. It is the natural route across curved geometry. In a similar but deeper way, an object moving through curved space-time follows a geodesic. A planet orbiting a star is moving as naturally and freely as it can through the space-time shaped by that star. From a simple spatial view, its path looks curved. From the fuller space-time view, it is following the equivalent of the straightest available path. This is the heart of the shift. Gravity is no longer a conventional force acting inside a fixed arena. The arena itself has become active. Space and time are not passive scenery. They respond to matter and energy. They curve, and that curvature guides motion. So when an apple falls, when the moon orbits Earth, when Earth travels around the sun, Einstein's theory says they are not merely being pulled by an invisible hand. They are moving through space-time whose geometry has been shaped by mass and energy. Gravity in this picture is not simply something happening in space. Gravity is what happens when space-time itself is no longer flat. General relativity can be gathered into one beautifully strange idea. Matter and energy tell space-time how to curve, and curved space-time tells matter and light how to move. That sentence sounds almost too neat for something so deep, but it is the heart of Einstein's theory. Gravity is not described as a normal force placed inside space, like a push, a pull, or a tug from an invisible thread. Instead, gravity is connected to the shape of space-time itself. The presence of matter and energy changes the geometry around it, and that changed geometry guides the paths of objects moving through it. This is why general relativity feels so different from Newton's picture. In Newton's view, Earth pulls on a falling stone. The sun pulls on Earth. Earth pulls on the moon. The language is clear and practical, and it works extremely well in ordinary situations. But in Einstein's view, there is a deeper description beneath that useful picture. A massive body does not simply reach across emptiness and yank another object toward it. It alters the structure through which that object travels. The sun, for example, contains an enormous amount of mass and energy. It does not sit in a completely passive, fixed space while throwing out a gravitational rope to Earth. Instead, the sun shapes the space-time around it. Earth then moves along a natural path in that curved space-time. To a distant observer looking only at space, Earth's path appears curved into an orbit. But in the fuller space-time picture, Earth is following the straightest path available through a geometry that is no longer flat. These natural paths are called geodesics. A geodesic is the closest thing to a straight line when the surface or space being travelled through is curved. On a flat sheet of paper, a straight line is easy to imagine, but on a globe, the shortest route between two distant places may look curved when drawn on a flat map. Long-distance aircraft routes often seem to arc across the map, especially near the poles. But they are not taking scenic detours just to admire Greenland. They are following efficient paths across Earth's curved surface. Space-time geodesics are deeper than aircraft routes because they involve time as well as space. Still, the basic idea is helpful. What looks curved from one limited perspective may be the natural straightest path in a larger geometric setting. A planet moving around a star is not constantly fighting to escape while being dragged inward by a physical cord. It is moving freely through curved space-time, following a geodesic shaped by the mass and energy of the star. Einstein expressed this relationship through the Einstein field equations. The name can sound rather intimidating, as if the universe has suddenly opened a very serious textbook at bedtime. But the core meaning can be stated gently. Space-time curvature is related to the amount and flow of energy and momentum. That is the essential idea. Energy and momentum include more than just mass sitting still. They include motion, pressure, radiation, and the flow of energy through a system. In general relativity, all of this contributes to the way space-time curves. The geometry of the universe is not shaped only by solid objects. It responds to the full physical content of reality. This is why light is also affected by gravity. Light has no rest mass, but it carries energy and momentum, and it travels through space-time. If space-time is curved near a star, a galaxy, or a black hole, then the path of light follows that curvature too. It is not that light needs to be pulled like a stone. It is that light travels along the available path through space-time, and those paths are altered by the presence of matter and energy. This point is important because it shows how far the theory has moved from ordinary force language. A rope can pull a box. A hand can push a door. A magnet can attract a piece of iron through an electromagnetic field. Gravity, in general relativity, is not quite like any of these. It is not just another influence moving through a fixed background. It is the behavior of the background itself. At the same time, curved space-time should not be imagined too literally. It does not mean space is bending into some visible higher dimension that could be seen from the outside like a dented sheet. The common rubber sheet image can help at first, but it can also mislead. A heavy ball on a rubber sheet makes a dip because Earth's gravity pulls it downward, so the analogy secretly uses gravity to explain gravity. A little cheeky, scientifically speaking. Real space-time curvature means that distances, times and paths are governed by non-flat geometry. It means that clocks can tick at different rates in different gravitational conditions. It means that the straightest possible routes through space-time can look like curved motion through space. It means that the structure of reality itself is affected by mass and energy. This does not make Newton wrong in the everyday sense. Newtonian gravity remains a superb approximation in weak gravitational fields and at speeds much slower than light. It can still describe a falling ball, the tides, the moon's motion, and much of the solar system with remarkable accuracy. General relativity does not throw that achievement away. It explains why Newton's picture works so well in ordinary conditions, while also showing what lies beneath it. The deeper framework is geometric. A falling object is not necessarily being forced away from its natural path. Very often, it is following that path. The strange part is that the path itself has been shaped by space-time curvature. The ground, the chair, or the floor interrupts that motion, and the body feels that interruption as weight. So gravity begins as the most familiar force in life, the thing that makes objects fall and bodies feel heavy. But in Einstein's theory, it becomes something far more subtle. Gravity is not merely an invisible pull inside the universe. It is the curved geometry of the universe guiding motion from within. The feeling of weight is one of the most convincing sensations in everyday life. It is there when the body sinks into a chair, when feet press against the floor, when a heavy bag pulls on the hand, and when the last few steps of a staircase begin to feel personally unnecessary. Weight feels so direct that it seems to settle the question immediately. Of course, gravity is a force. It can be felt in the bones, in the muscles, in the tired shoulders, in the slight complaint from the knees after standing too long. But this is exactly where ordinary experience can mislead. The feeling is real. The interpretation is the tricky part. When someone stands on Earth, it feels as if gravity is pulling them downward, and the body is simply resting there under that pull. In Newton's physics, this is a perfectly useful description. Earth exerts a gravitational force on the body, and the ground exerts an upward supporting force. The two balance so the person does not accelerate downward. That picture works very well for everyday calculations. In general relativity, though, the deeper interpretation changes. A person standing on the ground is not following their natural freefall path through space-time. The ground is preventing that motion. If the ground were suddenly removed, the body would begin to fall freely, following a geodesic through curved space-time. A geodesic is the natural path an object follows, where no non-gravitational force is pushing it away from that path. So strangely, standing still is not the most natural state in Einstein's picture. Falling is. That sounds backwards because daily life is spent on surfaces. Floors, roads, chairs, beds, hills, pavements, and inconveniently placed furniture all keep getting in the way of free fall. The body is almost always being supported by something. Because that support is constant, it feels like the ordinary condition of existing. But physically, the sensation of weight comes from being stopped from moving along the path gravity has laid out. The ground pushes upward. That upward push is not gravity, it is a contact force. At the microscopic level, it comes mainly from electromagnetic interactions between atoms in the floor and atoms in the body. The atoms in your feet do not pass through the atoms in the ground because the electrons around those atoms resist being compressed into the same space. Electromagnetism, not gravity, is responsible for the firmness of the floor. This is slightly rude of the universe, because the thing that feels most like gravity is partly caused by another force entirely. When standing on the ground, the body presses downward into the surface and the surface pushes upward in response. This upward support travels through the feet, legs, spine, and muscles. The body feels compression. That compression is experienced as weight. The chair beneath someone, the mattress beneath them, or the floor under their feet is continually preventing a natural fall, and the body senses that prevention. Now compare that with free fall. Imagine falling from a great height in a situation where air resistance is ignored. This is not a safety recommendation, merely a physics thought experiment with unusually poor holiday planning. During free fall, the body and everything nearby accelerate together. A dropped pen, a loose watch, and the person themselves all follow almost the same falling path. There is no floor pushing up against the feet. There is no chair resisting the body. For a brief time, the sensation of weight can disappear. Gravity is still there. In fact, gravity is the reason the fall is happening. But the feeling of weight has gone, because the support force has gone. The same principle applies in orbit. Astronauts aboard the International Space Station often appear to be floating because they are weightless, but they are not beyond Earth's gravity. The station orbits only a few hundred kilometers above Earth's surface, where Earth's gravitational influence remains strong. The station, the astronauts, their tools, their water droplets, and the occasional escaped snack are all falling around Earth together. They feel weightless because nothing is holding them up. This is why orbit is such a powerful clue. If gravity were felt in the same way as an ordinary force, astronauts should still feel a strong downward pull. But in their frame of reference, they float. They're in continuous freefall, moving fast enough sideways that they keep missing Earth. Gravity is shaping their path, but it is not producing the ordinary sensation of heaviness. Physicists describe the acceleration a person actually feels as proper acceleration. Proper acceleration is what an accelerometer would measure. It is the kind of acceleration associated with being pushed away from a natural freefall path. Standing on Earth, a person has proper acceleration because the ground is pushing upward and preventing free fall. In a freely falling spacecraft, proper acceleration can be close to zero, even though the spacecraft is moving through Earth's gravitational field. That distinction is subtle, but it is central. A person standing still on Earth feels acceleration in the general relativistic sense because they are being forced away from a geodesic. A person falling freely does not feel that same acceleration because they are following a geodesic. The falling person may be speeding up relative to the ground, but locally, inside their own small falling frame, they can feel weightless. This is one of the reasons the title must be understood carefully. Gravity is not real. Gravity is not a trick, a mistake, or a decorative rumour passed around by planets. It is real enough to hold worlds together, steer moons, bend light, shape galaxies, and alter time. But in general relativity, gravity is not felt in the same way as ordinary forces such as the electromagnetic contact force from the floor. The feeling of weight is mostly the feeling of being held away from free fall, so the floor beneath you is doing something more interesting than simply supporting you. It is interrupting your natural path through curved space-time. It is pushing upward, atom against atom, through electromagnetic resistance, giving the body the sensation that gravity is pulling down. And in a quiet way, this reverses the everyday story. The falling object is not the one being forced. The person standing still is. The solar system is familiar enough to picture, and precise enough to be dangerous to simple ideas. There is the sun at the centre, bright and massive, holding most of the mass in the entire solar system. Around it move the planets, each following its own path through space. Mercury circles close and quickly. Earth travels at a comfortable distance, taking 1 year to complete its journey. The outer planets move more slowly, their orbits wide and patient, as if they are in absolutely no rush to finish the lap. In Isaac Newton's picture, this arrangement is explained by force. The sun attracts the planets through gravity. Each planet has inertia, the tendency to keep moving forward, while the sun's gravitational pull constantly bends that motion inward. The result is an orbit. Earth does not fly away into space because the sun's gravity keeps changing its direction. Earth does not fall straight into the sun because its sideways motion carries it onward. That description is beautiful, powerful, and still extremely useful. But in Albert Einstein's general relativity, the same orbit is described in a deeper way. The sun does not simply sit in empty space and pull Earth with an invisible force. The sun's mass and energy curve the space-time around it. Earth then follows a geodesic through that curved space-time, meaning the natural path available to it when no force is pushing it away from that path. From an ordinary spatial view, Earth's orbit looks curved. It appears as though the planet is constantly being pulled around the Sun. But from the fuller space-time view, Earth is travelling as straight as it can through a geometry that is not flat. This is the quiet trick at the heart of the idea. A path can look curved because the space and time it passes through have their own curvature. The Earth is not trying to spiral into the Sun. It is not struggling against gravity like a moth trapped around a lamp. It is moving through space-time in a stable orbit because its motion and the Sun's curved geometry fit together. Earth's forward motion carries it onward, while the curvature around the Sun shapes the path into a long repeating journey. The orbit is not a failure to fall. It is free fall extended into a cosmic rhythm. This is why the solar system is such a useful place to think about gravity. It is not so extreme that Newton's physics breaks down completely. In fact, for most planetary motion, Newtonian gravity gives almost the same answers as general relativity. The gravitational fields are relatively weak compared with the regions near black holes, and planetary speeds are far below the speed of light. In these conditions, Newton's theory remains a superb approximation, and yet, almost is not quite the same as exactly. One of the most important clues came from Mercury, the smallest planet and the one closest to the Sun. Mercury moves quickly through the strongest gravitational field of any planet in the solar system. Its orbit is not a perfect circle. It is an ellipse, and the orientation of that ellipse slowly shifts over time. This gradual shifting is called precession. Some precession was expected. The gravitational pulls of the other planets, especially Venus, Earth and Jupiter, affect Mercury's orbit. Newtonian physics could calculate most of the shift very well, but after all known effects were included, a small extra amount remained. Mercury's orbit was precessing slightly more than Newton's theory predicted. The difference was tiny, but tiny differences matter in astronomy. A small, unexplained shift, measured carefully enough, can be a doorway into a new theory. The universe often whispers before it changes the textbook. The French mathematician Urbain Le Verrier had already shown how powerful orbital discrepancies could be. In the 19th century, irregularities in the orbit of Uranus helped lead Le Verrier and others to predict the existence of another planet beyond it. That planet, Neptune, was then observed in 1846. This was a triumph for Newtonian gravity. An unseen planet was found because its gravitational influence had disturbed the motion of a known one. So when Mercury's orbit showed a stubborn discrepancy, it was natural to wonder whether something similar might be happening. Perhaps there was another unseen planet closer to the Sun. A hypothetical planet named Vulcan was proposed, but it was never confirmed. The missing shift remained. General relativity solved it. Einstein's theory accounted for Mercury's extra precession, because space-time near the Sun is not exactly the arena Newton had assumed. Mercury, travelling close to the Sun, follows a geodesic through curved space-time. That curvature produces a small correction to the orbit, and the correction matched the unexplained part of Mercury's motion. It was one of the first major successes of general relativity. The result did not make Newton's theory useless. It showed where Newton's theory was an approximation. For Earth, Mars, Jupiter, and most ordinary solar system calculations, Newtonian gravity remains extraordinarily accurate. But Mercury, moving close to the Sun with precise observations available, revealed the difference between treating gravity as a force in fixed space and treating gravity as geometry in curved space-time. That is why the solar system is such an ideal middle ground. It is familiar enough for the mind to hold. The Sun, Earth, Moon, and planets feel almost domestic compared with black holes and galaxy clusters, and yet the motions are precise enough to expose the deeper structure of gravity. The solar system shows both truths at once. Newton's force explains an enormous amount. Einstein's geometry explains why the force picture works, and where it quietly begins to fall short. A planet in orbit is not resting on tracks. It is not tied to the Sun. It is not held in place by a hidden string stretched across space. It is moving freely through a curved space-time shaped by mass and energy. From far away, that free motion looks like a curve. From deeper within the theory, it is the straightest path the universe allows. Light is the universe's great messenger. It crosses space at the fastest speed allowed by nature, carrying images of stars, galaxies, nebulae, planets, and the long history of the cosmos. Almost everything astronomy knows about distant objects arrives through light, or through forms of radiation closely related to it. A star cannot be placed in a laboratory. A galaxy cluster cannot be politely asked to come closer. So light does the travelling instead, and scientists learn from what it brings. But light does something strange near massive objects. It bends. At first, that sounds as if it should not happen. A stone bends its path because gravity pulls on its mass. A planet orbits because it has mass and moves through a gravitational field. But light has no rest mass. It is not a little glowing pebble being dragged sideways in the ordinary sense. If gravity were only a force pulling on massive objects, the bending of light would be difficult to understand in a complete way. In general relativity, however, the bending of light makes deep sense. Light travels through space-time. If space-time is curved by matter and energy, then the path available to light is curved as well. The light is not being grabbed by an invisible hand. It is following the natural route through geometry that has been altered by a massive object. This is one of the clearest ways to see why gravity is not just a normal pull. A beam of starlight passing near the sun follows a slightly different path than it would if the sun were not there. The same idea applies on far larger scales. A galaxy, or an entire galaxy cluster, can bend the light from objects behind it. This effect is called gravitational lensing. The massive foreground object acts somewhat like a lens, not because it is made of glass, but because its gravity curves space-time and changes the paths of passing light. The result can be beautiful and scientifically powerful. A distant galaxy may appear stretched into an arc. Multiple images of the same background object can appear around a foreground galaxy. In especially neat alignments, light can form a ring-like pattern, known as an Einstein ring. It is not a physical ring floating in space, but an image created by curved light paths arriving from different directions. One of the first famous tests of this idea came during the solar eclipse of 1919. Einstein's general theory of relativity predicted that light from distant stars should bend as it passed near the sun. Normally, stars close to the sun's position in the sky cannot be seen because the sun is far too bright. But during a total solar eclipse, the moon blocks the bright solar disk, briefly allowing stars near the sun's edge to be photographed. Arthur Eddington and Frank Dyson organised expeditions to test this prediction. Observations were made from locations including the island of Príncipe and Sobral in Brazil. The basic idea was to compare the apparent positions of stars near the eclipsed sun with their normal positions when the sun was elsewhere in the sky. If the starlight bent while passing near the sun, the stars would appear very slightly shifted. The observation supported Einstein's prediction and helped make general relativity famous. Newspapers announced a revolution in science, and Einstein became, almost overnight, the most recognizable physicist in the world. For a theory about geometry, clocks, and careful measurements, this was quite a dramatic career move. Still, the eclipse results should be described carefully. They were historically important, but they were not a perfectly simple, flawless proof, arriving in one clean moment. The measurements were difficult. The photographic plates were affected by weather, equipment, and the limits of early 20th century observing. Later evidence would become far stronger, but the 1919 eclipse mattered because it showed that general relativity had made a bold prediction, and nature appeared to agree. Since then, gravitational lensing has become far more than a historical test. It is now a major tool in astronomy. The Hubble Space Telescope has captured striking images of galaxy clusters, bending and magnifying the light of much more distant galaxies behind them. These clusters can act like natural telescopes, allowing astronomers to study objects that would otherwise be too faint or too far away to examine in detail. Gravitational lensing also helps reveal dark matter. Dark matter does not emit light in the ordinary way, so it cannot be seen directly with telescopes. But it has gravity. When scientists map how light bends around galaxies and galaxy clusters, they can infer where mass must be located, even when much of that mass is invisible. The pattern of a lensing often shows that there is more matter present than ordinary stars, gas and dust can explain. Organisations such as NASA and the European Space Agency have used space telescopes and large surveys to study these lensing effects across the universe. The Hubble Space Telescope, the James Webb Space Telescope, and missions such as the European Space Agency's Euclid mission all contribute to the wider effort to map cosmic structure. Lensing turns curved space-time into a measuring tool, letting scientists investigate distant galaxies, dark matter distributions, and the web-like arrangement of matter on enormous scales. This is a remarkable reversal. What began as a strange prediction of Einstein's theory has become a practical method for exploring the universe. Curved space-time is not merely an elegant idea written in mathematical language. It can be photographed, measured, mapped, and used. Light bending near massive objects shows that gravity is not only about heavy things pulling other heavy things. Light has no rest mass, yet its path changes because the geometry through which it travels is changed. The effect is small near the Sun, larger near galaxies, and dramatic around galaxy clusters and black holes. So when light bends, it carries more than an image. It carries evidence about the shape of space-time itself, and in that bending, the universe quietly reveals that gravity is not just a force reaching across space. It is the shape of the road light follows. Time feels like the most reliable thing in the room. A clock ticks, a kettle boils, a shadow slowly changes position. A tired person tells themselves they will watch for only 10 more minutes, and then discovers that time has made other arrangements. In ordinary life, time seems to flow evenly everywhere, like a quiet river passing through the universe at the same steady pace for everyone. But general relativity says this is not quite true. Gravity changes time. More precisely, general relativity predicts gravitational time dilation. This means that clocks run at different rates depending on their position in a gravitational field. A clock closer to a massive body, such as Earth, runs slightly slower than a clock farther away from it. A clock near sea level runs very slightly slower than a clock on a mountain. The difference is tiny, far too small for human senses to notice, but it is real, measurable, and deeply important. This is one of the strangest consequences of Einstein's theory, because it shows that gravity is not merely something pulling objects downward, it affects the measured flow of time itself. In Newton's universe, time was absolute. It passed at the same rate everywhere, whether someone was standing on Earth, drifting through space, or orbiting the Sun. Gravity could change motion, but it did not change time. The clock of the universe ticked steadily in the background, untouched by planets, stars, or falling apples. Einstein's universe is different. Space and time are joined as space-time, and gravity is connected to the curvature of that space-time. If gravity is not just a force inside space, but a change in the geometry of space-time itself, then time cannot remain completely separate from it. Near mass and energy, space-time is curved, and clocks follow that curved structure. The rough idea is that time runs slightly slower, deeper in a gravitational field. Close to Earth, a clock is deeper in Earth's gravitational influence. Farther from Earth, the gravitational field is weaker, and the clock runs slightly faster by comparison. The clock is not broken. It is not being delayed by friction, bad batteries, or some cosmic administrator with a clipboard. It is measuring time correctly where it is. Another clock, placed at a different height, also measures time correctly where it is. The difference belongs to spacetime itself. This sounds like science fiction, but it has been tested. One important early confirmation was the Pound-Rebka experiment at Harvard University in 1959. Robert Pound and Glenn Rebka tested a prediction of general relativity using gamma rays travelling up and down a tower. The experiment measured how light changes energy as it moves through Earth's gravitational field, closely connected to the way gravity affects time. It was a delicate test, carried out over a height of only about 22 meters, yet it confirmed Einstein's prediction with impressive accuracy for its time. Later experiments used atomic clocks, which are extraordinarily precise. Atomic clocks do not keep time by swinging pendulums or turning gears. They rely on stable frequencies associated with atoms, making them sensitive enough to measure tiny differences in the rate of time. Modern measurements have shown that clocks at slightly different heights tick at slightly different rates. Even a height difference on the scale of ordinary human experience can be detected with sufficiently precise instruments. That is a quiet but remarkable fact. Place one excellent clock higher than another, and time itself runs a little differently for them. The effect near Earth is tiny. No one ages noticeably faster by standing on a chair, though it would be convenient if furniture offered that sort of dramatic service. But tiny does not mean imaginary. Physics is full of effects too small to feel and too important to ignore. Gravitational time dilation is one of them. It matters every day because of the Global Positioning System. Global Positioning System satellites orbit high above Earth and carry very accurate clocks. Their signals allow receivers on the ground to calculate position by comparing timing information from several satellites. For the system to work properly, timing must be extremely precise. Even very small clock errors can turn into large position errors. Two relativistic effects must be corrected. Special relativity says that moving clocks tick more slowly compared with clocks on the ground, because the satellites are moving quickly. General relativity says that clocks farther from Earth, in weaker gravity, tick faster than clocks on the ground. For Global Positioning System satellites, the gravitational effect is larger than the motion effect, so their clocks run slightly faster overall relative to clocks on Earth unless corrected. Without these corrections, navigation would drift by kilometers over time. A phone map, a ship, an aircraft, or a car sat-nav would gradually become less accurate. General relativity is not merely a theory written for black holes and distant galaxies. It is quietly involved when someone tries to find a cafe and is betrayed by roadworks. This makes gravitational time dilation one of the clearest clues that gravity is deeper than a downward pull. A normal force can change motion. A push can move a trolley. A pull can lift a bucket. But gravity changes something more fundamental. It changes how time is measured from one place to another. Near Earth, the effect is gentle. Near more massive and compact objects, it becomes stronger. Around a neutron star or near a black hole, gravitational time dilation can become extreme. A clock closer to such an object would run much more slowly compared with a clock far away. This is not because the clock is struggling. It is because space-time itself is shaped differently there. The everyday feeling of gravity is weight, but the deeper sign of gravity is geometry. It bends paths through space. It bends the path of light. And it changes the rate at which time passes. So gravity is not just the reason objects fall, it is part of the reason clocks disagree. The effect is small in ordinary life, but it is real enough to measure, real enough to correct, and real enough to guide modern technology. Every accurate satellite navigation signal carries, hidden inside it, a quiet confirmation of Einstein's idea. Gravity does not merely pull on the world, it changes the rhythm of time. Gravity can be hidden locally, but it cannot be hidden everywhere. That is the quiet lesson of tides. At first, tides seem like an ocean story. The sea rises and falls along coastlines. Harbours breathe in and out. Mudflats appear and disappear. Boats settle low in the water and later lift again, as if the whole ocean is slowly remembering the moon. But beneath that familiar rhythm is one of the deepest clues about what gravity really is. A tidal force is not simply gravity acting on an object. It is the difference in gravitational influence from one part of an extended object to another. That difference matters. If gravity acted exactly the same way on every part of something, then everything would accelerate together and the effect could disappear from local experience. This is what happens in free fall. A person falling freely, a pencil beside them, and the floor of a falling lift all share nearly the same motion. Locally, inside that small falling frame, gravity can seem to vanish. There is no feeling of weight, no obvious downward pull, no floor pressing upward. But if the falling object is large enough, or the gravitational field changes strongly enough across it, different parts do not follow exactly the same path. One side may be pulled slightly more strongly than the other. One end may be directed along a slightly different path through space-time from the other end. That difference creates stretching, squeezing, and relative motion. This is the tidal effect. Earth's ocean tides are the most familiar example. The moon's gravity affects the whole Earth, but it does not affect every part of Earth in exactly the same way. The side of Earth facing the moon is a little closer to the moon, so the moon's gravitational influence is slightly stronger there. The far side of Earth is a little farther away, so the moon's influence is slightly weaker there. These differences help create the tidal pattern in Earth's oceans. The sun also contributes to tides, though the moon has the larger tidal effect on Earth's oceans because it is much closer. When the sun, Earth, and moon line up during new moon and full moon, their tidal effects combine more strongly, producing spring tides. When the sun and moon are at right angles from Earth's point of view, their effects partly offset one another, producing neap tides. These names are not about the season of spring, which is a small mercy, because tides already have enough going on without needing calendar confusion as well. The ocean's response is not as simple as two neat bulges sliding around Earth. Continents, ocean depth, coastlines, seafloor shape, Earth's rotation, and friction all shape the real tides. In some places the tidal range is modest. In others, such as the Bay of Fundy in Canada, the difference between high and low tide can be enormous. A small gravitational difference becomes a large observable rhythm because the ocean is a moving fluid spread across a rotating planet. This is why tides are such a good way to understand gravity. They show that gravity is not only about a single object falling, it is about how nearby paths differ from one another. In general relativity, this becomes especially important. A freely falling observer can make gravity seem to disappear locally. Inside a small enough falling laboratory, the effects of gravity can look absent, at least for a short time and over a small region. This is part of Einstein's equivalence principle. Freefall feels weightless, because everything nearby is following nearly the same geodesic through curved space-time, but only nearly. If the laboratory is large enough, or if the gravitational field changes sharply enough, the illusion breaks. Two objects released side by side may slowly move closer together or farther apart. Different parts of the same object may be pulled along slightly different geodesics. This relative motion cannot be transformed away everywhere. It is not merely a matter of choosing a clever frame of reference. It is a sign of real space-time curvature. Tidal effects are the part of gravity that remains when the local feeling of gravity has been removed. Near Earth, these differences are usually gentle. A person does not notice their head and feet being influenced slightly differently by Earth's gravity, even though the difference exists. The body is far too small, and Earth's gravitational field changes too gradually over human height for the effect to be obvious. But instruments can measure such differences, and oceans respond to them on a planetary scale. Near a black hole, the same principle can become extreme. If an object falls toward a black hole, the side closer to the black hole may experience a much stronger gravitational influence than the side farther away. This difference can stretch the object along the direction of the fall and squeeze it from the sides. The informal name for this process is spaghettification. which sounds oddly playful for something so physically severe, as if the universe briefly hired an Italian chef with no safety training. The word is memorable, but the physics is simply tidal stretching. It is not a mysterious extra force invented for black holes. It is the same kind of difference in gravitational influence that helps raise tides on Earth, carried to a far more intense setting. Around small black holes, the tidal gradients near the event horizon could be enormous. Around very large supermassive black holes, the tidal forces at the event horizon can be gentler, though they may become extreme deeper in. This distinction matters because it shows that gravity is not just about strength. It is also about how quickly the gravitational field changes from place to place. A strong but nearly uniform gravitational field may be locally unnoticeable in free fall. A changing gravitational field produces tidal effects, and those reveal curvature. So gravity can be hidden in a small falling room, but not across the whole universe. It can vanish from local sensation, but not from the relations between neighbouring paths. It can stop feeling like a force, while still shaping how objects move relative to one another. That is the subtle distinction at the heart of the title. Gravity is not felt like an ordinary force by someone in free fall. A freely falling object follows its natural path through space-time. But space-time curvature still shows itself through tides, stretching, squeezing, and the way separate free-fall paths converge or diverge. The ocean rising beneath the moon is not just a coastal rhythm, it is curved space-time made visible in water. Black holes are where the geometry of gravity stops being gentle. Around Earth, space-time curvature is real but mild. It bends paths, slows time by tiny amounts, and helps guide the moon and satellites around the planet. Around the Sun, the curvature is stronger, enough to shift Mercury's orbit and bend passing starlight. But near a black hole, gravity is no longer a subtle correction to ordinary experience. It becomes the main shape of reality. A black hole is not simply an object with a very strong pull. It is a region where space-time curvature has become so extreme that, beyond a certain boundary, future paths lead inward. This boundary is called the event horizon. Once something passes inside it, there is no ordinary route back out, not because a wall blocks the way, but because space-time itself is arranged so that outward escape is no longer part of the object's future. That is a strange sentence, but it is the key idea. The event horizon is not a solid surface. A person falling across it, especially into a very large black hole, might not notice a sudden physical barrier at that exact boundary. There is no hard shell, no glass edge, no cosmic trapdoor with a little sign saying absolutely no refunds. The event horizon is a boundary in space-time. It marks the point beyond which light cannot escape to the outside universe. Since nothing can travel faster than light, anything inside the event horizon is cut off from sending signals outward. The black hole becomes black because light itself cannot return. This idea emerged from general relativity very quickly. In 1916, Carl Schwarzschild found the first exact solution to Einstein's field equations for a simple, non-rotating, spherically symmetric mass. Schwarzschild's work described the space-time around such an object, and revealed a boundary now associated with the Schwarzschild radius. At the time, black holes were not understood in the modern astrophysical sense, but the mathematics had opened a door to one of the strangest possibilities in physics. If enough mass is compressed into a small enough region, space-time can curve so intensely that an event horizon forms. It is important, though, not to imagine black holes as cosmic vacuum cleaners roaming through space and swallowing everything with dramatic enthusiasm. A black hole does not magically drag in the entire universe around it. From far away, its gravity behaves like the gravity of any object with the same mass. If the Sun could somehow be replaced by a black hole of the same mass, Earth would not suddenly spiral into it. Earth would continue orbiting in much the same way. Although the lack of sunlight would introduce several practical difficulties, beginning with almost everything. Black holes are extreme because their mass is packed into a very small region. Close to them, the curvature of spacetime becomes intense. Far away, they obey the same general gravitational rules as other massive objects. This matters because it keeps the physics grounded. Black holes are strange, but they are not magical. They are not holes in space in the ordinary sense. They are regions where gravity's geometric nature becomes impossible to ignore. Near a black hole, light paths are dramatically altered. Light can bend around the black hole, be trapped in temporary orbits, or fall inward beyond the event horizon. Time is altered as well. To a distant observer, a clock near the event horizon appears to run more slowly. Signals climbing away from the black hole lose energy and become stretched toward longer wavelengths. The closer something is to the horizon, the more extreme these effects become from the outside viewpoint. This is gravity not as an ordinary pull, but as a rearrangement of paths, clocks, and causality. Causality means the order of cause and effect, the structure of what can influence what. Near a black hole, that structure changes profoundly. Outside the event horizon, there are still possible future paths that lead away. Inside it, all future directed paths point deeper inward. It is not just that escape would require a stronger rocket, it is that the geometry no longer provides a future route back to the outside. That is why black holes sit so naturally inside a discussion of gravity as geometry. They reveal what happens when space-time curvature becomes extreme. They show that gravity is not merely a force acting across space, because in a black hole, space and time themselves behave differently. The paths available to matter and light are changed at the deepest level. For many years, black holes were mostly mathematical and theoretical objects. Today they are supported by many lines of evidence. Scientists observe stars orbiting unseen massive objects. They detect intense radiation from hot matter, swirling around compact regions. They measure gravitational waves from black hole mergers, and most famously, the Event Horizon Telescope has produced images of the glowing material around supermassive black holes. In 2019, the Event Horizon Telescope collaboration released an image of the black hole at the centre of the galaxy Messier 87. The image showed a bright ring of emission around a dark central shadow, shaped by extreme gravity and light bending near the event horizon. In 2022, the collaboration released an image of Sagittarius A star, the supermassive black hole at the centre of the Milky Way. These images are not photographs of the event horizon as a surface. They're observations of light from hot material around the black hole, distorted by the curved space-time nearby. Even so, they are remarkable. They make the geometry visible. They show the shadow cast by a region from which light cannot escape, surrounded by matter heated to extraordinary temperatures as it moves through the black hole's gravitational environment. Black holes also reveal the limits of current physics. General relativity describes the space-time outside and around black holes with extraordinary success. But deep inside, near what the mathematics calls a singularity, the theory appears to reach a boundary of its own. A singularity suggests that the known equations are being pushed beyond where they can give a complete physical description. Most physicists do not treat that as the final word. The deepest interior of a black hole likely requires a theory that can join general relativity with quantum mechanics, a theory of quantum gravity. Such a theory does not yet exist in a complete, experimentally confirmed form. So black holes are not only laboratories of extreme gravity, they are also signposts pointing toward what physics still does not fully understand, and that makes them quietly perfect for this question. If gravity were only a force, black holes would be merely places where the force becomes very strong. But they are more than that. They are places where paths close, light is trapped, time changes, and the future itself tilts inward. They are the edge of geometry. Gravity can be so gentle that it feels like stillness, and so violent that it sends ripples through space-time itself. These ripples are called gravitational waves. They are not waves in air, like sound. They are not waves on water, rising and falling across the surface of a pond. They are not electromagnetic waves. like light, radio waves, or X-rays. Gravitational waves are travelling distortions in spacetime, produced when massive objects accelerate in dramatic ways. In ordinary life, moving objects do not create gravitational waves strong enough to notice. A person walking across a room technically contributes to the gravitational story of the universe, but not in a way that will trouble any observatory. The waves are fantastically tiny by the time they reach us, even when they are born from some of the most powerful events in the cosmos. To make gravitational waves large enough to detect, nature usually needs something extreme: black holes orbiting each other, neutron stars spiraling together, or massive objects moving with enormous acceleration. Albert Einstein predicted gravitational waves as a consequence of general relativity. If gravity is the curvature of space-time, and if massive objects can move and accelerate, then the geometry of space-time should not remain perfectly still. Changes in that geometry should travel outward. A pair of black holes orbiting each other does not simply sit in a fixed gravitational arrangement. Their motion stirs space-time, sending ripples away at the speed of light. This is one of the clearest ways to understand why gravity is not just a normal force. In Newton's picture, gravity was an attraction between masses. In Einstein's theory, gravity is the behaviour of space-time geometry. So a gravitational wave is not a force signal travelling through a material substance. It is a dynamic change in space-time itself, moving outward from a changing gravitational source. There is no air being compressed, no water surface rising, and no hidden cosmic jelly wobbling politely in the background. Space-time itself is what is changing. For many decades, gravitational waves remained a prediction rather than a direct observation. They were mathematically expected but extraordinarily hard to detect. The reason is not that they are weak at their source. A merger between black holes can release an astonishing amount of energy in gravitational waves. The problem is distance. By the time the waves spread across space and reach Earth, their effect is almost unimaginably small. The first strong evidence came indirectly from a remarkable system called the Hulse-Taylor binary pulsar. In 1974, Russell Hulse and Joseph Taylor discovered a pair of neutron stars orbiting each other, one of which is observed as a pulsar. A pulsar is a rotating neutron star that sends out regular beams of radiation, rather like a lighthouse, though admittedly one of the least cosy lighthouses ever conceived. Because the pulses arrived with extraordinary regularity, scientists could measure changes in the orbit with great precision. Over time, the two neutron stars were slowly spiraling closer together. Their orbit was shrinking in exactly the way general relativity predicted if the system was losing energy through gravitational waves. The waves themselves were not directly detected, but their effect was visible in the changing orbit. It was like noticing ripples had carried energy away by watching two dancers gradually move closer together on a dark floor. The direct detection came much later. In 2015, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves from the merger of two black holes more than 1 billion light-years away. The signal was incredibly brief, but it matched the pattern predicted by general relativity. Two black holes had spiraled together, merged into one, and sent a tremor through space-time that crossed the universe before passing through Earth. The observatory that detected it is often called LIGO, short for the Laser Interferometer Gravitational Wave Observatory. Its method is beautifully precise. Laser beams travel along long perpendicular arms, reflect from mirrors, and return to be compared. If a gravitational wave passes through, it very slightly stretches space in one direction and compresses it in another, changing the relative lengths of the arms by an extraordinarily tiny amount. The change is far smaller than the width of an atom. That is the astonishing part. Scientists are not watching great waves roll visibly through a machine. They are measuring one of the smallest changes human technology has ever detected, caused by one of the largest events in the universe. It is a lovely example of physics being both absurdly delicate and completely enormous at the same time. the first direct detection opened a new kind of astronomy. Until then, most astronomy had depended on light and other electromagnetic radiation. Telescopes collected visible light, radio waves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. Gravitational wave astronomy allowed scientists to observe the universe through space-time itself. Since that first detection, the Laser Interferometer Gravitational Wave Observatory, scientific collaboration, has worked alongside other observatories, including Virgo in Europe and Kagra in Japan. Together, these instruments help detect and confirm gravitational wave events from black hole mergers, neutron star mergers, and other compact cosmic systems. When multiple observatories detect the same event, scientists can better estimate where in the sky it came from and what kind of source produced it. One especially important event involved merging neutron stars. Unlike black hole mergers, neutron star mergers can also produce light and other electromagnetic signals. That allows astronomers to combine gravitational wave observations with telescope observations, creating what is called multi-messenger astronomy. It means the same cosmic event can be studied through different forms of information, like hearing thunder and seeing lightning from the same distant storm. Gravitational waves matter for this story because they make space-time feel almost tangible. Not tangible in the sense of something that can be held in the hand, but tangible in the scientific sense. Measurable, active, responsive, and real. Space-time is not an empty stage where gravity performs. It participates. It curves, stretches, compresses, carries waves, and changes when massive objects move. That is a very different picture from gravity as a simple invisible pull. A gravitational wave does not say that one object is tugging another across a void in the old way. It says that the geometry of reality can be disturbed and that disturbance can travel. It says black holes can merge in darkness, beyond the reach of ordinary sight, and still leave a passing whisper in the distances between mirrors on Earth. So gravity is not merely a force reaching across space. It is space-time becoming dynamic. And sometimes, when the universe moves violently enough, that motion travels outward as a ripple, crossing billions of light years before briefly passing through everything, including the planet beneath you, the room around you, and the quiet space where you're listening now. Newton was not wrong in the way an old map is wrong. He was right in the way an old map can be astonishingly useful, even after a satellite image reveals more detail. The coastline may be rougher than the map shows. The mountains may have more hidden folds. The scale may not be perfect at every point. But for many journeys, the old map still gets you where you need to go. Newtonian gravity is like that. General relativity gives a deeper description of gravity. It explains gravity as the curvature of space-time rather than a conventional force acting across a fixed background. It accounts for bending light, gravitational time dilation, black holes, gravitational waves, and the tiny extra shift in Mercury's orbit. In the deepest modern picture, Einstein sees farther than Newton, and yet Newton's theory is still used constantly. The reason is approximation. Physics does not always need the deepest possible theory to make an accurate prediction. It needs the theory that is accurate enough for the conditions being studied. Newtonian gravity works extremely well when gravitational fields are weak, when speeds are low compared with the speed of the light, and when the required precision is not pushed to the extreme edge. Most of everyday life lives comfortably inside that range. A ball thrown through the air does not require the full machinery of curved space-time to describe its path. A builder calculating loads in a structure does not usually need general relativity to understand how weight presses downward. A bridge, a crane, a falling stone, a swinging pendulum, and a ladder leaning against a wall can all be treated with Newtonian physics so successfully that adding Einstein's equations would be a bit like using a space telescope to find the television remote. Technically impressive, not always necessary. Newton's framework remains central in engineering because it is clear, practical, and accurate in ordinary conditions. Forces, masses, accelerations, moments, stresses, and loads can be calculated with methods rooted in classical mechanics. Buildings stand, machines run, aircraft fly, and vehicles brake because engineers can apply these approximations reliably. General relativity is true at a deeper level, but the correction it would add to most everyday engineering is so tiny that it has no practical effect. The same is true in ballistics and projectile motion. The path of a thrown object, a launched shell, or a falling package can usually be described very well using Newton's laws, with extra details such as air resistance, spin, wind, and drag added as needed. The mathematics may become complicated, but it does not usually become relativistic. The object is moving far too slowly compared with light, and the gravitational field is far too weak for spacetime curvature corrections to matter in any noticeable way. Even many spacecraft calculations can begin with Newton. Space agencies use highly refined models, and relativity does matter in some precision contexts, but Newtonian gravity remains enormously useful for understanding orbits, escape velocity, transfers between planets, and the motion of spacecraft through the solar system. The basic idea of a spacecraft falling around Earth or moving from one orbit to another can be understood beautifully through Newton's laws. Ordinary planetary motion is similar. For most planets, most of the time, Newton's law of gravitation gives excellent results. The planets move through weak gravitational fields compared with the regions near black holes, and their speeds are small compared with the speed of light. That is why Newtonian mechanics was able to predict celestial motion with such success for centuries. It was not a lucky guess. It was a brilliant description of nature within a very wide domain. General relativity becomes necessary when the situation leaves that comfortable domain. Near massive compact objects such as neutron stars and black holes, gravity is too strong for Newton's approximation to capture the full picture. Space-time curvature becomes intense. Light paths bend dramatically. Time dilation grows large. The event horizon of a black hole cannot be properly understood with Newtonian gravity alone, because it is not just a place where the pull is strong. It is a boundary in space-time where the future paths of light and matter are altered. General relativity also becomes necessary for high-precision timekeeping. The global positioning system depends on timing so accurate that relativistic effects cannot be ignored. Satellite clocks are affected by both their motion and their height above Earth. Special relativity and general relativity make corrections that are tiny by human standards, but essential for navigation. Without them, position estimates would gradually drift by large amounts. Across cosmological scales, general relativity is also essential. The expansion of the universe, the behavior of light across vast distances, gravitational lensing by galaxy clusters, the structure of space-time on the larger scales, and the evolution of the cosmos all require Einstein's framework. Newton can describe many local motions, but the universe as a whole needs a deeper theory. This is how science often works. A newer theory does not always erase an older one. It shows why the older one worked, where it works, and where it reaches its limit. Newtonian gravity is not rubbish because general relativity exists. It is an approximation of extraordinary power. It is one of the greatest intellectual achievements in history, and it remains woven into the practical world. The phrase, "gravity is not really a force," must therefore be handled carefully. It does not mean Newton was foolish. It does not mean generations of physicists were simply confused. It does not mean that treating gravity as a force is useless. In the Newtonian framework, gravity is a force, and that framework works beautifully across a huge range of experience. The deeper point is that Einstein revealed another layer. At ordinary scales, gravity behaves enough like a force that the force picture is often the right tool. At deeper scales, gravity becomes geometry. It becomes the curvature of space-time, the shaping of paths, the slowing of clocks, the bending of light, and the quiet structure behind free fall. Newton gave the universe a law of attraction. Einstein showed that the attraction was also a clue to the shape of reality itself. Gravity is the odd one out. That does not mean gravity is less important than the other forces. In everyday life, it feels like the most obvious force of all. It gives weight to the body, keeps oceans on Earth, holds moons near planets, and gathers stars into galaxies. But when modern physics compares gravity with the other fundamental interactions, gravity begins to look very different. The other three fundamental interactions are electromagnetism, the strong nuclear interaction, and the weak nuclear interaction. Together, these three are described by the Standard Model of particle physics, the great framework that explains much of the behavior of particles and forces at the subatomic level. The Standard Model is not a theory of everything, but within its domain it is one of the most successful scientific structures ever built. It describes the particles that make up ordinary matter and the interactions that govern much of their behavior. Electromagnetism is the most familiar of the three non-gravitational interactions. It acts through electric charge. Charged particles can attract or repel one another, and electromagnetic fields carry the influence of those charges through space. Electromagnetism is responsible for light, electricity, magnetism, chemistry, and the contact forces that make solid objects feel solid. When a hand presses against a table, the atoms in the hand do not pass through the atoms in the table because electromagnetic interactions resist that compression. In a very practical sense, electromagnetism is why the everyday world has texture. It is why chairs support people, why shoes press against pavements, why magnets stick to fridges, and why ordinary matter does not behave like a ghostly fog passing through itself. Gravity may make a body feel heavy, but electromagnetism is doing much of the local pushing back. The strong nuclear interaction is much less visible in daily life, but it is essential to the existence of matter. It acts mainly inside atomic nuclei and within particles such as protons and neutrons. Its deeper description involves quarks and gluons. Quarks are fundamental particles that make up protons and neutrons, and gluons are associated with the strong interaction that binds quarks together. The strong interaction also helps hold atomic nuclei together, overcoming the electromagnetic repulsion between positively charged protons. Without the strong nuclear interaction, atoms as we know them could not exist. Hydrogen might still be simple enough to imagine, but the richer chemistry of carbon, oxygen, iron, calcium, and all the other heavier elements would not be possible in the same way. Stars, planets, bodies, bones, and the slightly alarming variety of things found at the back of a kitchen cupboard all depend on stable atomic nuclei. The weak nuclear interaction is also subatomic, but it does a different kind of work. It is involved in certain forms of radioactive decay and in processes that allow particles to change identity. It plays a crucial role in nuclear reactions inside stars, including the chain of events that helps the sun shine. It is less intuitive than electromagnetism, and less obviously structural than the strong interaction, but it is deeply important to the way matter evolves and transforms. These three interactions are treated through quantum field theory in modern physics. That means particles and forces are described using fields that exist throughout space, with interactions taking place through quantum processes. The full details are complex, but the broad picture is clear enough. Electromagnetism, the strong interaction, and the weak interaction all fit within a quantum framework. Gravity does not fit so easily. At the particle level, gravity is extraordinarily weak compared with electromagnetism. The electromagnetic repulsion between two protons is vastly stronger than their gravitational attraction. In the world of atoms and particles, gravity is usually so tiny that it can be ignored. Chemistry, electricity, magnetism, atomic structure, and nuclear physics are not mainly governed by gravity. They are governed by the other interactions, and yet gravity dominates the universe on large scales. The reason is that gravity accumulates. Mass and energy are always associated with gravitational influence, and there is no simple negative mass that cancels positive mass in ordinary situations. Electromagnetism, by contrast, has positive and negative charges. Large objects usually contain nearly equal amounts of positive and negative electric charge, so their electric effects mostly cancel out over large distances. A planet is not usually one giant electric charge, thankfully. The lightning bills would be unmanageable. Gravity does not cancel in the same ordinary way. Every piece of mass and energy adds to the gravitational field. A rock has gravity, a mountain has gravity, Earth has gravity, the sun has gravity, galaxies have gravity. Across astronomical scales, the tiny weakness of gravity is overcome by the enormous accumulation of matter and energy. That is why gravity shapes planets, stars, galaxies, galaxy clusters, and the cosmic web. This creates a strange division in physics. On the smallest scales, gravity is usually negligible. On the larger scales, it becomes the main architect. The deeper difficulty is that gravity is described in a different language. The other interactions are described as quantum fields acting within spacetime. Gravity, in general relativity, is not simply another field placed inside spacetime. It is the curvature of spacetime itself. Matter and energy shape geometry, and geometry guides motion. That difference makes gravity hard to combine with quantum field theory. Quantum field theory assumes a spacetime background where fields operate. General relativity says the background itself is dynamic. It bends, evolves, carries waves, and responds to matter and energy. Trying to make these two views work together is one of the great unresolved problems in theoretical physics. This is where ideas such as quantum gravity, string theory, and loop quantum gravity enter the conversation. These are attempts to describe gravity in a way that can fit with the quantum nature of the rest of physics. String theory suggests that fundamental ingredients may be tiny extended objects rather than point-like particles. Loop quantum gravity explores whether spacetime itself may have a discrete quantum structure at extremely small scales. Other approaches study related possibilities, sometimes using black holes, cosmology, or mathematical models as clues. But there is no complete experimentally confirmed final theory yet. General relativity remains extraordinarily successful for gravity, and quantum field theory remains extraordinarily successful for the other interactions. The difficulty is not that either theory is casually broken. The difficulty is that each is too successful in its own domain to ignore, and yet they do not merge smoothly into one finished picture. So gravity is different in more than one way. It is weaker than the other interactions at small scales, stronger in its cosmic influence, and described not as a conventional force inside spacetime, but as the geometry of spacetime itself. That is why the title has a sharper meaning now. Gravity is not really a force in the same sense as electromagnetism or the nuclear interactions. It can behave like one in Newtonian physics, and that description remains wonderfully useful. But in the deeper Einsteinian picture, gravity belongs to the shape of reality. The other forces act within the stage. Gravity changes the stage. Gravity is not only the reason a dropped object falls. On the larger scales, it is the quiet builder of the universe. The same influence that gives weight to a body also gathers gas into stars, pulls dust into planets, draws stars into galaxies, and helps arrange galaxies into enormous clusters and filaments. Look outward far enough, and the universe does not appear as a smooth mist of matter spread evenly in every direction. It looks more like a vast web, with galaxies gathered along long threads, dense clusters shining where those threads meet, and immense, darker voids lying between them. This structure is often called the cosmic web, and gravity is the main reason it exists. In the early universe, matter was spread more evenly than it is today, but not perfectly evenly. There were tiny differences in density, small regions where matter was slightly more concentrated than elsewhere. Gravity amplified those differences over time. A region with a little more matter had a little more gravitational influence, so it attracted more matter, which made its gravity stronger, which attracted still more. Slowly, patiently, across hundreds of millions and then billions of years, gravity turned small unevenness into structure. This is one of the most important things gravity does. It does not simply pull objects downward. Downward is only a local idea, meaningful near the surface of a planet. In space, gravity pulls matter together from all directions. It gathers, it concentrates, it takes drifting gas, dust, dark matter, stars and galaxies, and shapes them into larger arrangements. Stars begin this way too. A star forms inside a cold cloud of gas and dust, often called a molecular cloud. These clouds can be enormous, stretching across many light years, and they contain mostly hydrogen, along with helium, dust grains, and traces of heavier elements. If part of the cloud becomes dense enough, gravity begins to pull it inward. The gas contracts. As it falls inward, its density rises. Its temperature rises too because gravitational energy is being converted into heat. At first, the forming star is a protostar, a young object still gathering material from its surroundings. Gravity keeps compressing the gas, and pressure builds in the center. Eventually, if the central temperature and pressure become high enough, hydrogen nuclei can begin to fuse into helium. This is nuclear fusion, the process that powers main sequence stars like the Sun. Fusion does not begin because the gas decides to become dramatic. It begins because gravity has squeezed the material so intensely that the center becomes hot and dense enough for nuclear reactions to occur. Gravity is the hand that lights the star, though not by striking a match. More like by patiently compressing a cosmic cloud until the laws of physics have no choice but to start glowing. Once a star is stable, it lives in a balance called hydrostatic equilibrium. This is one of the great balancing acts in astrophysics. Gravity pulls the star inward, trying to make it collapse. Hot plasma and radiation pressure push outward, resisting that collapse. In a stable star, these two influences balance. The star does not explode apart and it does not collapse inward. It shines because inward gravity and outward pressure have reached a long-lived agreement. The Sun is in hydrostatic equilibrium right now. Its gravity pulls its enormous mass inward, while the energy produced by nuclear fusion in its core helps support it from within. This balance has lasted for billions of years and will continue for billions more. Every ray of sunlight reaching Earth is connected deep down to this balance between collapse and pressure. Gravity also builds planets. Around young stars, leftover gas and dust form rotating disks. Within those disks, small particles collide, stick together, and gradually grow. Dust becomes pebbles. Pebbles become larger bodies. Larger bodies attract more material through gravity. Over time, planets can emerge from this process of accretion. The details are complex, and collisions can be messy, but the broad principle is simple. Gravity helps small things become larger things. On even larger scales, gravity gathers stars into galaxies. A galaxy can contain millions, billions, or even trillions of stars, along with gas, dust, stellar remnants, dark matter, and central black holes. Spiral galaxies like the Milky Way rotate in graceful disks. Elliptical galaxies can appear more rounded or stretched, filled with older stars moving in many directions. Irregular galaxies show less tidy shapes, because the universe is under no obligation to keep everything symmetrical for human satisfaction. Galaxies themselves gather into groups and clusters. The Milky Way belongs to the local group, which includes the Andromeda Galaxy and many smaller galaxies. Larger galaxy clusters can contain hundreds or thousands of galaxies bound together by gravity. Beyond that, clusters and galaxies trace the cosmic web, forming immense filaments across space. But to understand this structure properly, visible matter is not enough. One of the major clues came from galaxy rotation curves. In the 20th century, astronomers including Vera Rubin and Kent Ford studied how stars move around the centres of galaxies. Based on the visible matter alone, the outer parts of galaxies were expected to orbit more slowly than they did. Instead, many stars far from galactic centres were moving as if much more mass existed than could be seen. This unseen mass became part of the evidence for dark matter. Dark matter is not dark because it is merely hidden behind dust, or because it is ordinary matter painted in a very committed shade of black. It is called dark because it does not emit, absorb or reflect light in the usual detectable ways. Its presence is inferred from gravity. Galaxy rotation curves, gravitational lensing, galaxy cluster behaviour, and large-scale cosmic structure all point toward more gravitational mass than visible matter can explain. The particle nature of dark matter remains unknown. Scientists do not yet know exactly what it is made of. It may involve particles not included in the ordinary matter described by the standard model of particle physics, but no final answer has been experimentally confirmed. This is an important boundary in current science. The gravitational evidence for dark matter is strong, but the identity of dark matter is still unresolved. Modern observatories continue to investigate this mystery. The European Space Agency's Euclid mission is designed to map the dark universe by studying galaxy shapes, gravitational lensing, and the expansion history of the cosmos. The National Aeronautics and Space Administration space telescopes, including the Hubble Space Telescope and the James Webb Space Telescope, also contribute to understanding galaxies, cosmic structure, and distant matter across cosmic time. Gravitational lensing is especially important because it allows scientists to map mass through the way it bends light. A galaxy cluster can distort and magnify the images of galaxies behind it. By studying those distortions, scientists can estimate where mass lies, even when much of that mass is invisible. Once again, gravity reveals what light alone cannot show. On cosmic scales, then, gravity is not just something that makes objects fall. It is the architect of structure. It turns small density differences into galaxies. It pulls gas into stars. It helps build planets. It holds galaxy clusters together. It traces the invisible presence of dark matter. It shapes the web-like pattern of the observable universe. And in the language of general relativity, this means the universe is not built by a simple force acting on a fixed stage. It is shaped by space-time geometry across enormous distances and timescales. Matter and energy curve space-time, and that curved space-time guides the motion of matter and light. Gravity begins as the feeling of weight beneath your body, but followed far enough outward, it becomes the reason the universe has structure at all. General relativity is one of the most successful theories ever created. It has explained the orbit of Mercury, the bending of starlight, gravitational time dilation, black holes, gravitational waves, and the large-scale behaviour of the universe with astonishing precision. It has survived tests in the solar system, in satellite navigation, around compact objects, and across cosmic distances. For more than a century, it has remained one of the pillars of modern physics, not because it sounds elegant, though it certainly does, but because it keeps agreeing with nature. And yet physicists do not generally believe it is the final complete description of gravity in every possible condition. That may sound strange at first. If a theory works so well, why not simply declare victory, close the notebook, and allow the universe to enjoy a quiet evening? The reason is that science does not only ask whether a theory works in the places where it has been tested, it also asks where the theory begins to strain, where its equations point toward extremes, and where another part of physics becomes impossible to ignore. General relativity is extraordinarily successful within its tested domain. It describes gravity as the curvature of space-time, and it does this with remarkable power. But there are certain places where the theory seems to reach its own edge. These include the deepest interiors of black holes, the earliest moments of the universe, and situations where gravitational physics and quantum physics both matter at the same time. Black holes show this problem very clearly. Outside the event horizon, general relativity describes black holes extremely well. It predicts how light bends, how time slows, how matter orbits, and how gravitational waves are produced when black holes merge. Observations from the Event Horizon Telescope and detections by gravitational wave observatories have supported this picture in dramatic ways. But deep inside a black hole, the mathematics of general relativity points towards something called a singularity. A singularity is often described loosely as a point of infinite density, but that phrase needs care. In physics, a singularity is better understood as a sign that the mathematical description has reached an extreme limit. The theory is being pushed into a region where its own equations no longer provide a complete physical answer. That does not necessarily mean there is a literal physical object with infinite properties sitting at the centre of a black hole. Infinite values in physics often indicate that the model has broken down, not that nature has calmly decided to become impossible. They are like warning lights on the dashboard of a theory. The theory is still useful for the journey, but it is telling you that the road ahead cannot be described with the same map. A similar issue appears when scientists think about the earliest moments of the universe. General relativity is central to modern cosmology. It underlies the expanding universe, the Big Bang model, the behaviour of space-time on large scales, and the formation of cosmic structure. But as the universe is traced backward toward its earliest known state, matter becomes hotter, denser, and more extreme. Eventually, quantum effects can no longer be ignored. This is where the difficulty deepens. General relativity describes gravity and spacetime as smooth, geometric, and dynamic. Quantum physics describes matter and energy in terms of probabilities, fields, discrete interactions, and uncertainty. Each framework is enormously successful in its own domain. General relativity works beautifully for planets, stars, galaxies, black holes, and the expanding cosmos. Quantum theory works beautifully for atoms, particles, light, chemistry, electronics, and the microscopic structure of matter. But when gravity is very strong and distances are extremely small, both theories seem necessary at once. The interior of a black hole is one example, the earliest universe is another. In these places, a complete theory would likely need to describe gravity in a way that is compatible with quantum principles. That deeper theory is often called quantum gravity. Quantum gravity is not one single finished theory. It is a broad research goal. The attempt to understand gravity in a way that fits with the quantum nature of the rest of physics. Many approaches exist, and none has yet become a complete experimentally confirmed final answer. String theory is one such approach. It suggests that the most fundamental ingredients of nature may not be point-like particles, but tiny extended objects whose different patterns can correspond to different particles. In some versions, gravity appears naturally within the mathematics, which is one reason string theory has attracted so much interest. It is ambitious, mathematically rich, and still not experimentally confirmed as the final description of nature. Loop quantum gravity is another approach. It explores the possibility that space-time itself may have a quantum structure at extremely small scales, rather than being perfectly smooth all the way down. In this view, geometry may be built from more basic quantum ingredients. Again, it is a serious and active line of research, but not yet an experimentally verified replacement for general relativity. There are also semi-classical approaches, where matter is treated using quantum theory, while gravity is still treated through a classical space-time background. Semi-classical gravity can be useful in certain problems, including some ideas connected with black hole radiation and quantum fields in curved space-time. But it is not usually regarded as the final full theory of quantum gravity. It is more like a bridge, and bridges are useful, even when they are not the whole continent. Research into these questions happens across many institutions and collaborations. CERN is central to particle physics, even though it is not a gravity laboratory in the simple sense. The Perimeter Institute in Canada has been important for theoretical physics, including quantum gravity research. The Max Planck Institute for Gravitational Physics, also known as the Albert Einstein Institute, studies general relativity, gravitational waves, and related questions. Universities around the world continue to investigate black holes, cosmology, string theory, loop quantum gravity, and the mathematical foundations of spacetime. The important point is not that general relativity has failed in some ordinary way. It has not. It remains one of the most accurate and profound theories science has ever produced. Its unresolved limits do not weaken its success where it has been tested. They show something more interesting and more honest. A theory can be extraordinarily powerful and still incomplete. This is a familiar pattern in science. Newtonian gravity was not useless because Einstein later revealed a deeper picture. Newton's theory remains an excellent approximation in many conditions. In the same way, general relativity may one day be understood as part of an even deeper framework, not discarded, but explained more fully, not proven foolish, but placed inside a larger understanding. That is how scientific progress often feels when viewed calmly. It is not always a clean replacement of wrong by right. It is often a widening of context. A theory works, then a deeper theory explains why it works, where it works, and where it stops being enough. Gravity is one of the clearest examples of this. It begins as the simple feeling of weight. Then it becomes Newton's force between masses. Then it becomes Einstein's curved space-time. Then, at the edges of black holes in the earliest universe, it becomes an unfinished question pointing toward a theory not yet fully known. The more precisely gravity is understood, the stranger it becomes. Not because science makes it vague, but because science removes the comfortable simplifications. The familiar downward pull becomes free fall. Free fall becomes geometry. Geometry becomes space-time. And space-time, at its deepest limits, may be asking for a new language. Gravity is not less real because the story is unfinished. It is real enough to reveal where physics still has to go. Gravity is not really a force in the deepest modern sense because general relativity describes it as the curvature of space-time and the motion of objects along natural paths through that curved geometry. That does not mean gravity is fake. It does not mean Newton was wrong in some simple or foolish way. In Isaac Newton's physics, gravity can still be treated as a force of attraction between masses, and that description works beautifully in everyday conditions, weak gravitational fields, and many practical calculations. It can describe falling objects, projectiles, tides, planets, and spacecraft with extraordinary usefulness. For much of ordinary life, Newton's gravity is not merely good enough, it is magnificent. But Einstein revealed a deeper layer beneath it. The journey began with the familiar feeling of weight, the sense that gravity is simply pulling everything down. Galileo Galilei showed that falling itself follows surprising rules, and that without air resistance, objects fall with the same acceleration regardless of mass. Newton then united falling apples and orbiting moons through universal gravitation, showing that Earth and sky obeyed the same physical law. Orbits became continuous falling, and yet Newton's theory still carried the strange problem of action at a distance, as if gravity could reach across empty space without a visible mechanism. Then Einstein's equivalence principle changed the question. A freely falling observer can feel weightless, even while gravity is shaping their motion. Hermann Minkowski's space-time gave relativity a new language, and general relativity turned gravity into geometry. Objects follow geodesics, the natural paths through curved space-time. Light bends, Mercury's orbit shifts. Clocks run at slightly different rates in different gravitational conditions. Tides reveal curvature across extended regions. Black holes show geometry pushed to an extreme, and gravitational waves show space-time itself, rippling outward from violent cosmic events. The evidence is not only philosophical. The bending of starlight, gravitational lensing, satellite clock corrections, Observations of black holes and detections of gravitational waves all support the general relativistic picture. Gravity is not just a downward pull, it changes paths, time, light, and the large-scale structure of the universe. The feeling of weight is mostly the ground, a chair, a floor, or some other surface preventing free fall. In free fall, gravity can vanish locally from experience, even though space-time curvature remains measurable across larger regions. So gravity is both deeply familiar and profoundly strange. It is the quiet reason things fall. Planets orbit, stars form, time changes, light bends, and the universe gathers itself into structure. The floor beneath you may feel like proof that gravity is pulling you down, but physics suggests something stranger. You are being held away from the natural path space-time has laid out beneath you.